Yeah, am I audible to you?
Yes, ma'am. We are audible.
Sorry, you're muted. I couldn't hear you.
Yes, madam, you are audible.
Okay, fine, fine, fine. Okay. So, is the screen visible to both of you?
Yes, ma'am, it is visible.
Okay, thank you. So, good evening, everyone. So, this is the second live tutorial session on fundamentals of electronic materials and devices. So, we had our first session last week on Tuesday from 6 to 8, and a few people had joined. And those who have attended the session might be knowing what will be the usual course of action. So, in this live tutorial session, what we will be doing is we will be solving questions that are similar to your assignment questions. So, we'll be taking questions from your non-graded assignments from this year as well as from previous years. And in case you have any doubts from your previous assignments also, you can post it to me and I'll find the answer to those questions and get back to you. So speaking about me, I am Santara Krishnan. I'm a research scholar under the PMRF scheme in Soft Matter and Complex Fluids Lab at IATM. So this is the mail ID I mentioned in case you find any doubts from the previous year sessions also. You can mail to me asking your doubts, and in case many people have doubts on a specific topic and you give me the topic beforehand, I can prepare and I can have a short session on that as well. So on that note, I think we can start this week's questions without delay. So first is, this is actually a gate question that helps us in understanding all the concepts that is required for solving the questions of this week. So the question is that the simplified energy band diagram of an intrinsic semiconductor at thermal equilibrium is shown. So thermal equilibrium, they're taking it as 300 Kelvin, and in the accompanying table that is here, they have given four combinations, and you have to select which one of the four columns correctly represents the listed parameters. And it's given, assume the same effective mass for electrons and holes. So basically what we have to do is that an energy band diagram is given to us, and from this diagram you have to select whether column 1 gives their proper definition, column 2, column 3, or column 4 gives us the proper definition of band gap, electron affinity, and work function. So like, since only three of us are there, I would like it to have a kind of be an interactive session. So please take a few moments to try to answer and get back to me with the answers that you have identified. Yeah, the definitions you have to find out. What is band gap from the figure? What is electron affinity from the figure? And what is work function from the figure? Please take as much as time, and in case you have been making notes, you can refer that as well. Yeah,
It's D, D, ma'am.
sorry.
D, D, option D, column 4.
Okay, and the other person? Yeah, like, is the other person also getting the same answer? Like column 4, will it be column 2 or column 4? I want you to check again. Like you mentioned, it's column 4, right? So electron affinity and work function, what would be the difference in that case?
Yeah, it may be column 2 now.
Yeah,
Maybe column.
yeah.
Yeah.
So I'll just explain this question. So basically the thing is that whenever we are talking about energy band diagrams, we'll be having something like this. This is known as the valence band. And in the valence band, what is that? At normal temperature, that is at equilibrium temperature, it will be completely filled and the conduction band will be completely empty. And whenever we are providing a sufficient energy, e.g., what happens? Electrons from the valence band will be excited to the conduction band, leaving behind holes. For usual materials like metals and insulators, etc., and semiconductors, we will be defining them as valence band maximum and conduction band minimum. But in case of discrete materials, what happens is that instead of energy bands, they will be having energy levels. So then they will be called highest occupied molecular orbital and lowest unoccupied molecular orbital. So in between the conduction band maximum and the valence band maximum and conduction band minimum, we have something known as Fermi level. Then we have something known as ionization energy, work function, electron affinity, and this particular region is the vacuum energy. So if you are defining EVAC is the vacuum level, EA is the electron affinity as I already mentioned, WF is the work function, IE is the ionization energy, EG is the band gap, and here we have the expansion of what is mentioned here. So this is actually the abbreviation expansions in case you are confused in the diagram. So now we'll explain one by one. So what is the Fermi level or EF? So basically the Fermi level, it is the highest energy level that the electron can occupy at absolute zero temperature. We know usually that the electron will be present only inside the valence band and conduction band. But when we are studying related to quantum mechanics, what they say is that there is a probability of finding electron somewhere in between. That is a max highest energy level can be obtained. That is, there is a possibility of finding an electron in between the valence band and conduction band. That is the highest energy level that the electron can occupy. It lies between these two bands, and at this particular region the electrons will be in their lowest energy state, that is the Fermi energy. Then we have the band gap. So band gap is basically the energy difference between the valence band maximum and the conduction band minimum, and an electron can move from this valence band to conduction band only when an energy that is equal to Eg is supplied to the material. Then work function. Work function is defined as the minimum quantity of energy required to remove an electron to infinity from the surface. So that is the amount of energy that is, we know at Fermi level there is a probability of finding an electron, right? So to remove an electron from here to the E vacuum, that is the energy that's known as work function. Then we have energy difference between psi. Psi is the electron affinity, right? Between the bottom of the conduction band and infinity is known as the electron affinity. So bottom of the conduction band and energy vacuum. So this particular region, it is known as chi and it is known as electron affinity. So this is the basic concepts that we'll be using in the upcoming questions. So first we have a few conceptual questions and after that we will move on to the numerical part. So does anybody have any doubt with regard to this diagram, the expansions or anything? So in that case, if you have any doubt, please do ask right now. A few other people have also joined, I think. Yeah. So actually we have not started solving any numerical questions. We are just giving a recap of what is the like work function, what is all those other things like work function, electron affinity, conduction band maximum, valence band minimum, all those things we are just giving a recap. So in case anybody has any doubt with this diagram, please to ask right now. So we have explained what is the Fermi level, what is band gap or energy gap, then what is work function, and then what is chi or electron affinity. All those things we have mentioned. And once you are clear with these concepts, you will come back to this question and you will be able to answer. So first, if you see here, what will be the option? So first is we have to say what is band gap. So band gap means that it is the energy difference between the valence band maximum and conduction band minimum. So in this question, they have not marked what these values are. Hence, we have to take that this is the valence band maximum and this is the conduction band minimum. So between them, we have delta E1, that is our band gap. So delta E1 being band gap, we have two options. Either we can take it as column 2 or column 4, right? So delta E1 we have got. Next, we have told what is electron affinity. That is the energy that we require to remove an electron from the Fermi level to vacuum level. To Fermi level to vacuum level, what it will be? Sorry, the conduction band maximum minimum to the vacuum level, what it will be? That is the electron affinity. That is, an electron will be here and the amount of energy that is required to remove it. Then what will be the answer? Hello, am I audible to you? Am I audible? Why no one is responding? Am I audible to all of you?
Yes, madam.
Okay. Yeah. So what will be the amount of energy that is required to remove an electron from this point to vacuum level is the electron affinity. In that case, it will be delta E2 minus delta E1, right? And finally, we have the work function. Work function means the amount of energy that we require to remove an electron from the Fermi level to vacuum level. So in that case, it will be delta E2 minus delta E1 by 2. So delta E2 is this much and delta E1 by 2 will be half of it. So is it clear? Therefore, the answer will be column 2. So first we have a band gap. Band gap, I'm sure everyone will be clear because this is the valence band maximum and this is the conduction band minimum, and between them we have the band gap. That is correct. That everyone knows, I guess. Next is electron affinity. Electron affinity means that we are removing an electron from the conduction band minimum to the vacuum level. So the distance will be from this point to this point. So how do you take that? Delta E2 minus delta E1. So that is this case. Next is work function. Work function means that we have to remove an electron from the Fermi level to the vacuum level. So what will be this? We know this entire thing is delta E2, and this small region will be delta E1 by 2. Suppose you subtract delta E1 by 2 from delta E2, that is delta E2 minus delta E1 by 2 will give us the work function. So I hope this concept is clear to all of you. Is it clear?
Yes, ma'am.
Okay. So next is, which of the following describes the relationship between carrier concentration and band gap for an intrinsic semiconductor? So we have four options. We have to select from that the relationship between carrier concentration. So the word here is intrinsic semiconductor, right? So we have something known as Ni. If you have gone through the lectures, you will be sure that you have seen something known as intrinsic carrier concentration, Ni. So what equation connects intrinsic carrier concentration Ni to Eg? So there is one equation which has both Eg and Ni. So can anybody tell me which equation that is connecting Ni and Eg?
Exponential relation, ma'am.
Sorry?
Exponential relation.
Yes, exponential relation. So that is the correct answer. So basically, how do you know that it's an exponential relation? Suppose you have an equation. So this is the equation that connects Ni with Eg. So Ni is equal to root of Nc Nv e power minus Eg by 2 times Kb into T. So basically the relationship between Ni, and suppose we are taking this to be a constant, then we can write Ni is proportional to e power minus Eg by some other constant, and hence it is Ni proportional to e power something. We can say that they will be having an exponential relation. So that is the answer to this question. Exponential relation is the answer. So is this answer clear to all of you? I want everybody to respond, and in case anybody is having any doubt, please do unmute and ask. These contents are actually from week 2, so you've already submitted those assignments and things. So I think you will be already knowing these equations and all. The answer is exponential relation. That is because considering NC and V to be constant, we can write Ni proportional to e power Eg by something. Since it is e power Eg, we are telling that this is an exponential relation. So that is the answer to this question. Does anybody have any doubts? Please do ask. Like I think Harish responded right now, right? So what about Jayaprakash, Malarvidi and Rajesh? Is it clear to you?
Yes, ma'am, it is clear.
Yeah.
Yes, ma'am.
Yeah. Okay. So next is, which of the following statements is true? Note more that one answer might be correct. So first is, addition of trivalent impurities to a semiconductor creates many bound electrons. At high temperature, mobility decreases because of lattice scattering. Increase in carrier concentration results in decrease in semiconductor resistivity. Amphoteric dopants always act as donors. So they are asking which of the following statement is true, and they have themselves mentioned that more than one answer will be correct. So you have to find out of these which statements are true.
Then B and C are correct.
Yes. So what about the others? Do you have the same opinion, or yeah, please. B and C are correct. That is the right answer. Does anybody have any other opinion, right? A or D might be correct, or any doubts regarding that?
What is meant by amorphoteric dopants?
Amphoteric dopants means that with respect to the element they are being doped, they have capability of acting both as donors and as acceptors. That is amphoteric doping. So that is, suppose an example is that for amphoteric dopings, we are doping silicon into gallium arsenide. Suppose we have a semiconductor gallium arsenide and we are doping it with silicon. Suppose gallium is doped with silicon, what happens? They will act as donors. And if silicon replaces the arsenic part, it will act as acceptors. So the same silicon has the capability of acting both as acceptor and as donor based on which element they are replacing. So in gallium arsenide, if you take and you're replacing first silicon with gallium, you're exchanging those both. Then then what happens? Silicon becomes donor. And suppose silicon is replacing the arsenic part, what happens? Silicon becomes acceptor. So this D won't be correct based on what I just explained. D won't be correct. And here if you see in case of A, what they are telling that they are adding trivalent impurities to a semiconductor creates many bound electrons. So most semiconductors that will be in our question will be in case of tetravalent. That is silicon if we are taking trivalent impurities means it is already having an electron deficit, right? Therefore, it won't create bound electrons. And whatever they do is we never create bound electrons. These electrons will be free of conduction, right? Therefore, A will also be wrong. So in that case, B and C will be correct. At high temperature, one is mobility decreases, that is conductivity decreases because of lattice scattering. Large number of electrons and holes will be generated, and the electrons as they move inside the material, what happens? They get scattered from other atoms. So and as a result, mobility will decrease. But at the same time, then whenever we are increasing carrier concentration, the conductivity increases. Conductivity increases means that resistivity will decrease. So is it clear? So this is the
Yes, madam.
explanation. Yeah. With increasing temperature, phonon concentration increases and causes scattering. So this lowers the mobility. Then semiconductor conductivity is directly proportional to carrier concentration. At high temperature, what happens is that both of them will start acting. And there will be a competition between whether more lattice scattering is happening or more conduction is happening. That is what decides the final conductivity of your semiconductor. Yeah. So is it clear?
Yes, madam.
Yeah. So next is degenerate semiconductors generally exhibit dash. More than one answer might be correct in this case too. So we have something known as degenerate semiconductors, and they have two characteristics, and these characteristics are given in the option. So what are those characteristics?
And one, that means A and C. I found that
Yeah,
I hope that they are
yeah, A
okay.
and C is correct. Yeah. What about the others? Do you feel that A and C are correct, or is there any other option that is a possibility? Degenerate semiconductors basically means that it is a semiconductor when we are adding a large or a high amount of doping, and because of this doping, what happens? Large number of trans states will be created, and eventually the Fermi level becomes merged with the valence band or conduction band. So degenerate semiconductors actually behave as metals itself. They do not have an active band gap. They will start acting as metals itself. That is the case with degenerate semiconductors. Therefore, we can say they have a very high level of doping, and the Fermi level will lie inside the valence band or the conduction band. So basically, typical dopant concentrations will be in the range of parts per million or parts per billion, and they will form individual energy levels that are non-degenerate normal semiconductors. But when the dopant concentration increases, what happened? There will be large number of energy levels, and they will be starting to overlap with each other, and they will start forming bands. So this happens when doping is in the range of 10 power 19 and 10 power 20. So then what happens, as there are a large number of energy level and they become bands, the dopant energy level will start merging with the valence band or conduction band, and hence the Fermi level will lie inside the band. So that is what happens with degenerate semiconductors, and they behave as metals. So is it clear to you?
Yes, madam.
Yeah, what about the others? Is it clear? In case you have any doubt with these concepts, please do ask. So next is a tutorial question, that is a numerical one. You'll have to start solving, and I want all of you to answer, not only one person, all of you should actually work out and give me the answer. So the question is, the band gap of intrinsic gallium arsenide is 1.43 and electron affinity is also given. Assuming the effective masses of electrons and holes at the band gap edges are equal, what is the work function of the material? Give your answer in electron volt. So first, what is the equation that connects band gap and the effective masses of electrons and holes? So something for a Fermi level, we have an equation, right? Something that connects the effective mass and Fermi level, that equation we have. So once you know that equation, you can find Fermi level. Once you get Fermi level is given to you, electron affinity is also given to you. From that, you can find the work function. Band gap. So first, somebody has to give me what is the equation that connects Fermi level and effective masses. So you can take a few minutes to check your notes and see if you have that equation with you. Can anybody give me the equation? Anybody? In case no one is giving, I'll give the equation. So basically what I just mentioned here is that, see, band gap is given. So this is our material. Suppose this is the gallium arsenide diagram you imagine. Band gap is given as 1.43. So this portion you know, this band gap entire thing you know, it is 1.43. And electron affinity, the Chi value also you know, 4.07. 4.07 Chi value also you know. Electron affinity you know, band gap you know. And they are asking us to find the work function. So if you know the value of Fermi level, based on that Fermi level, you will be able to find out the work function. So this band gap, you know, electron affinity, you know, and they are asking us to find the work function. If you know the value of EFI, you will be able to calculate the work function. So to use that, what equation we will use? Here it is also given, all this data is also given to you. That is the effective mass of electron and hole is equal. Eg is 1.43 and psi is 4.07. And this is the equation that you have to use. With respect to valence band, that is EV means energy of valence band maximum and EC is the energy of conduction band minimum. So either you can use this equation or you can use this equation. For convenience, we will be using this equation. So now that you have the equation, can you please substitute and tell me the answer? So from that diagram, once you know the value of EFI, we will be able to find out the work function. EC minus EFI means that from this diagram, what we will be getting? EC minus EFI means that this small distance you will be knowing, right? The small distance you know. Once you know the small distance, adding this with that small distance will give us the work function. So basically, this small region you are going to find out. So this is the small region that you are going to find out right now. Once you find this one, then this is 2. 1 plus 2 will give us the work function. So to find out 1, we have an equation. So what is basically 1 from this diagram? 1 is EC minus EFI, right? EC minus EFI will give us 1. So adding 1 and 2, we will get the work function. So we have an equation for EC minus EFI. So that is this equation. EC minus EFI you can take from this equation. So hence you can use EC minus EFI as Eg by 2 plus 3 by 4 kT ln Me by Mh star. And Me is equal to Mh star they have already given. Therefore, this will become as ln1. So what is ln1? And can you please solve and let me know the answer? EC minus EFI.
Ma'am, EC minus EFI will be 0.713, 715.
Yeah. What about the others? Somebody unmuted. Please find out EC minus EFI. Yeah, tell me. So this will be the substitution
EC
steps.
minus.
Yeah. Is the same answer you are getting?
So yes, ma'am.
Yeah.
Uh,
And
so
now
work
you have,
function is
yeah,
4.715.
yes, exactly. 4.785 it will be. 4.07
Okay.
plus
Uh,
0.715.
yes. It is just calculation.
Yeah.
Yeah, right.
So is this question clear to you? First, we have to find EC minus EFI, and once you add this EC minus EFI to our this chi value, we will be getting the work function. So how did you understand that? We got it from that particular diagram. So first we have to find the small distance, and then this is already given to us. To find the small distance, we can use the equation that connects energy of conduction band minimum and the energy of intrinsic Fermi level. So once you have the EC minus EFI value, adding that to the chi will give us the work function. So I hope it's clear to all of you. In case you have any doubt, please ask right now. Jayaprakash Malarvidi, is it clear to you?
Yes, ma'am.
Yeah. So next is two semiconductors X and Y have the same effective density of states, both at the conduction band and valence band. The intrinsic area concentrations of X and Y are 300 Kelvin are 2 into 10 power 13 and 10 power 10 cm power minus 3 respectively. The band gap of X is given as 0.7. We have to find the band gap of Y. So again, it is an equation that connects Ni, root of NCNV and band gap. So you have two semiconductors. For those two semiconductors, you have to write down those two equations and then divide them. And only thing that is missing here is Eg2, that is of Y, or you can write as Egi, either is fine. So we have to find the value of Egi. So what is the equation that connects Ni and Eg and NCNV? An equation we all know, right? Connecting Ni, NCNV and Eg. So that equation you have to use here. What will be the equation? Does anybody know the equation?
It is under root NC by NV into E raised to EG by 2 kt.
Yeah. So this is the equation. Ni is equal to root of NCNV e power minus Eg by 2 times kt. So this Ni you have to write for X and you have to write for Y. And that both you have to divide. So it's all given to us, right? Ni1 is given, Ni2 is given, Eg1 is also given. And they have told that NCNV, root of NCNV is same for both of them. So they will basically get cancelled. So in that case, what will be Ni1 by Ni2? So for X and Y, you have to write down this equation and then divide them both. Finally, you will get the value of Eg2 or Egi. So can you please take a few minutes and find the answer and let me know? So basically what I just mentioned is you have to write down this equation. That is Ni1 by Ni2. Here I am denoting x as 1 and y as 2. And they have told that NC1, NV1 and NC2, NV2, these two are same, equal to each other, right? So they will get cancelled. Therefore, Ni1 by Ni2 is equal to e power minus Eg1 by 2 kT and minus Eg2 by 2 kT. Now you have to just substitute whatever is given to you. You have to take the value of K in electron volt. So what will be K in electron volt? 8.617 into 10 power minus 5. And when you substitute that, you will get the value of Eg2. So can you please solve and let me know? If you have started solving, it would look something like this. So check if your substitutions are right. Even if the final answer goes wrong, you can do it again and check, but your substitutions should be correct. Then probably you'll arrive at the correct answer. So this is this part you can solve, this solve, you can solve and this solve. And only what remains is that e power minus Eg2 by 2 times kT. And from that we can calculate. So Harish and three people are there. One person left, I think. So rest all are you solving in the same way? Rajesh, Harish, and Jayaprakash. So are you able to solve in the same route or are you getting stuck anywhere? Please let me know. So at least till this step, are you getting correctly? So are you getting it? Yeah, so we got e power minus Eg by 2 times kT as 6.5917 into 10 power minus 10. And if you take ln on both sides, it will become ln e power something becomes that constant. Suppose we are writing ln e power a is basically a. So what happens? We can write this ln 6.59 will be 21.14. And since we are adding ln to both sides, what happens? This becomes that constant alone, minus Eg by 2 times kT. And now we know 2 times kT already we know. K is a constant, temperature is 300, and we will finally get the value of Eg2. Are you able to understand? Hello?
Yes, ma'am, we are able to understand.
Yeah. Okay.
Ma'am, is it possible that we cancel out e raised to 2 kT on both of the side?
No, that we cannot cancel. That is because here already we have a constant in the top, right? Minus Eg1 is a constant, right?
Mm.
Here this is e power
I think we
minus
can cancel
eg1
out
by 2 times kt. So in case you're cancelling and getting the correct answer, I don't know. But usually this is the method that we do.
yeah.
Because this is e
Because I
power
get
something.
8 point something. Yeah,
Okay, fine, fine.
when I cancel out, I get 8 point something. So I think it is not correct answer.
Not
8
correct. The basically thing
means
is
anything
that it is e power some
means
constant, right?
Mhm.
So that e power, this e power something will give us a constant value that we cannot cancel out. Since here we have some variable and here we are having a constant. If eg1 is equal to eg2, then we can cancel out. Only in that case we'll be able to cancel out. Otherwise we cannot cancel out. Yeah. So we will get approximately 1.1 electron volt.
Okay, okay.
Yeah. So I hope it's clear now.
Yes, ma'am, it is clear.
Yeah, and whenever you're doing things related to e power something, better to take log on both sides. Because when you take log on both sides, this constant alone will stay, this ln will also go, this e will also go. Only constant will remain.
Yeah, yeah.
Constant will remain. Yeah.
Yes, yes.
Yeah, so next question is given that the effective masses of electrons and holes in silicon are 1.10 MeV and 0.55 MeV respectively, find the location of the intrinsic Fermi level at 300 Kelvin. MeV is the rest mass and the band gap is also given as 1.1. So in the previous question, we had seen an equation that connects EFI and EV, right? So that equation you have to use here.
Hmm.
Yeah. So this is basically the equation that you have to use. EFI is equal to EV plus half EG minus 3 by 4 KT ln ME star by MH star. Here instead of giving ME star and MH star, they are telling that ME star is equal to 1.10 ME and MH star is equal to 0.55 ME. And that ME and ME will get cancelled. It will become 1.10 and 0.55. So that is how you have to move. So can you please use this equation and start solving? So when you substitute, you will get something like this 1.1 by 2 minus 3 by 4. K is a constant, 300 is given to us, and ln, those two values they have given to us 1.10 ME and 0.55 ME. ME and ME will get cancelled. So when you solve this part 3 by 4 KT ln ME by ME star by MH star, you will be getting 0.013438. Yeah. Are you getting the
Yes,
same
ma'am.
answer? Yeah. And finally,
Huh.
what will be the
Yes,
answer?
yes. Plus 0.55. We have to subtract it from
Yeah.
0.55.
Yeah. So basically it will be, so basically what you got, EF5 minus AV is equal to 0.54. Let us assume approximately 0.54.
That means,
Yeah. So EF is
yes, yes.
basically EV plus 0.54. So it is 0.54 electron volt
Above
above
valence.
valence band. So that will be the answer. Yeah. So I hope it's clear to all of you. We'll move on to the next question. So this is basically what I told. EFI we have got here, and EFI plus something, that is EV plus something, we got EFI. Therefore, it will be 0.54 electron volt above the valence bandage. So next is, which of the following materials can be considered transparent to visible light? That is, out of these four options, they should not absorb, they should transmit. So you can decide that based on the what factor we will be using here in order to decide whether the material is transparent or absorbing.
It is galvanium arsenide, madam.
No, it's not gallium arsenide. Like what factor?
CDA, CDS.
No,
Direct and indirect band gap.
no. Direct and indirect band gap is not the factor. Actually, the band gap value you have to see. That is what decides whether a material is okay. Basically, we all know solar cells, right? And most common material used for solar cell is silicon. That we all know, right?
Still.
Yeah. So why do we
Yes,
use
yes.
silicon? We use silicon because it is capable of absorbing all type of light, right? UV, visible, everything it is capable to absorb. That is why silicon is most commonly used in solar cell. So what is the band gap of silicon? We all know that it is 1.1 electron volt, right? So what does that
Yes, ma'am.
mean actually? So that is the criteria that we use here to see whether a material, suppose silicon was transparent, means that it is not absorbing. It is just letting through it. Light is coming inside and it is going outside. It is not being absorbed. So silicon we cannot use, right? But where silicon is using means that silicon is capable to absorb. So silicon is not the answer. So out of the other three, how do we decide? We decide based on their band gap value. So basically, band gap means what? This particular energy we have to give so that electrons that are sitting here can jump to the conduction band. Suppose this band gap value is 1.1 electron volt in case of silicon. That is the minimum energy that we should give. If you are giving 1.2, 1.3, 3, 4, 5, whatever what happens, it will again get excited. So minimum should be 1.1. So when you see here, you can see that silicon is 1.1, cadmium sulfide is 2.42, gallium arsenide is 1.42, and silica here is 7.5 to 9.6, much higher than all these three, right? Now we have to use an equation and find the relationship between energy band and wavelength. So which equation we will be using to find the relationship between energy and wavelength?
E is equal to H.
Yeah, E is equal to h nu. From E is equal to h nu, we can write nu as c by lambda. We can write hc by lambda. And this hc is a constant. That constant is 1240. And this E will be in electron volt, lambda will be in nanometer. And now what happens when you substitute, what we will get? Gallium arsenide, we already know that it is 1.42, right? And cadmium sulfide was 2.42. And when you substitute all of these energy values, we will get below 873, it is capable to absorb. Below 512, it can absorb. But what happens for silica? It can absorb only below 165. So this is what I already mentioned. So I'll show you once more. Huh. Here I told that silicon is 1.1 electron volt, right? When I am substituting that 1.1 in this equation, that is 1240 by 1.1, I will get 1107 nanometer, which means that from this graph, if you see below 1107, that is somewhere around here, this entire part that silicon is absorbing. It is not transmitting. Transmitting means that just going inside and going outside. It is entirely being absorbed in case of silicon. And for other materials like gallium arsenide and cadmium sulfide also, if you substitute, it will be below 873. 873, any value it can absorb. Below 512, any value of sufficient amount it is capable to absorb. But if you see silica, what it can absorb only below 165 nanometer. 165 means almost entire range is over, right? Nothing is left to absorb. So it is transparent. It is just letting the light go inside and come out. It is not absorbing. So based on this equation, we can decide whether it is absorbing or not. And if you substitute and see 1.12 means you will get 1107. If you substitute 1.5, you will get some another value that is less than this value, less than 1107. Somewhere inside this graph you will get, which means that silicon can absorb everything less than 1107. Gallium arsenide can absorb everything less than 873, somewhere over here. Cadmium sulfide, everything less than 500. But what happens for silica? It can absorb only below 165. Every wavelength that is above 165, it will just randomly go inside and come out through the other side. It won't absorb. Therefore, what will be the answer then? Silica, right? Is it clear or should I go explain again?
So ma'am, it means that we have to find out whatever for whatever the material. If it is below 200, then it is transparent.
Yeah, below 200 means only from 0 to 200 it is absorbing, right? 0 to
Yeah.
200 means what it will be? It will be in UV range usually. Visible starts from where to where? 400 to 700,000 and all is visible, right?
7.
Yeah, so here they are asking
Yes, ma'am.
transparent to visible, right? Which means that if the band gap is such that it is not able to absorb above 400, means that it is transparent. If your material is not absorbing above 400, means that it is transparent to visible light. Is it clear now?
Yes, madam. Yes, ma'am.
Yeah. So that is the case. So this equation is very important. It will be useful in many scenarios, not only for this equation, for but many things this will be useful. 1240 by E. And here you have to note 124, lambda will be in nanometer, E will be in electron volt. This is like a shortcut equation that you can use everywhere. Instead of going for these lengthy calculations, you can just use 1240 by E. E will be in electron volt. I hope it's clear to you. A major part of the visible spectrum is transmitted through. 165 means that it is not absorbing any visible. Hence, silica is considered visible to transparent light. Sorry, transparent to visible light. So, is it clear to you?
Yes, ma'am.
Yeah. So, next is in an intrinsic semiconductor, they are given that Nc greater than Nv. Where will be the Fermi level located at room temperature? Take Eg as band gap. All choices are given with respect to top of the valence band. Again the same equation. EFI minus EV is equal to that equation you have to use. And earlier we were using the equation which had ME star and MH star. Here we should not use that equation, but similar equation with NC and NB. So this is the equation that you have to use here. From this equation only the other equation was derived. The earlier we used instead of NC and NB, here we used ME star and MH star, right? So this is actually the base equation that we use. From this one, we can derive the ME star and MH star value equation. So based on this equation, they are telling us NC is greater than NV. In that case, where will the Fermi level be located at room temperature? Above, below, at and at Eg by 2. So the idea, the basic hint here is that if NC is greater than NV, ln of a positive number greater than 1 we can get. So that will be a positive value. Suppose if NV is greater than NC, this ln NV by NC will become negative. So based on that, this sign will change. Then the location will change in the figure. So here they are telling that NC is greater than NV. So suppose you are taking that NC as 10 and NV as 5. It will become ln2. ln2 will be positive, right? So in case ln2 is positive, what happens? This part will remain negative itself. It won't change sign. And here they are told that all choices are given with respect to top of valence band, which means that our valence band we are taking as the reference, and this EV will be 0. Then what is the case? EFI is equal to half of EG minus,
Answer is
yeah, B.
B answer.
Yes, it will be below Eg by 2. So given that Nc is greater than Nv, therefore the value of Ln will be positive. If the top of the valence band is considered as reference, then we can write Ev is equal to 0 electron volt. And then if we evaluate the expression, EFI is equal to half of Eg minus something, some constant. So it will always be below Eg by 2. So is that clear? Suppose it
Yes,
was
yes.
ulta. Suppose we are telling that Nc less than Nv. Then what happens? This will become negative. Ln this term will become negative and this will change to a plus sign. And when it changes to plus sign, what that means? It will be above Eg. That is the case.
Above it.
Yeah. So this is a conceptual question. There is nothing to solve here. Just Ln value you have to check. That's all. So next is for an intrinsic semiconductor, room temperature electrical conductivity is given to us. If the electron and hole mobility is 0.75 and 0.06, the intrinsic carrier concentration at room temperature we have to find out. Simply directly you can use the equation for conductivity here. So what is the equation for conductivity for an intrinsic semiconductor?
Any mu plus PE mu H.
Yes. Sigma is equal to NE mu E plus PE mu H. So in this equation, you have to substitute. Electron and hole mobility is given to you. E value is a constant. Sigma is also given to you. You have to find the value of Ni. That is what you have to find. So please substitute and let me know. Sigma is given or other values are given. We have to find the value of Ni. Yeah, somebody unmuted.
And 7.71 into 10 power 12.
Okay, let me check. Yeah, 7.78 into 10 power 12 per meter cube. That's the right answer.
Hello.
Hello? Yeah. Am I audible?
And
Hello? Hello? Yeah, the answer is correct.
Yes, ma'am, you are audible.
yes, ma'am.
Yeah,
Audible.
yeah. So that is the answer.
Yes, ma'am.
Yeah, 7.78 into 10 power 12 per meter
Yes,
cube is the
ma'am.
answer. Yeah. So is the other person also getting the same answer?
Yes, ma'am, I got 7.2 into 10 raised to minus 12.
12. Yeah.
So it is approximately
Yeah.
here.
Okay. So next we'll go to the other question. The intrinsic area concentration of silicon at 300 Kelvin is 10 power 10 cm power minus 3. A sample of silicon is doped with phosphorus of concentration 10 power 15 and boron of concentration 10 power 16. Assume complete ionization of all atoms. Which of the following is true for this kind of semiconductor? So here a material is being doped with both p-type and n-type. That is something known as compensation doping. So when a case of compensation doping is there, how do we decide what is the number of electrons or what is the number of holes? First we have to see which concentration is more. Here which is more?
Whole concentration.
Yeah, boron concentration will be more. Boron is a p-type and phosphorus is an n-type. So here from the equation if you see 10 power 15 and 10 power 16, boron atoms will be more, right? So the final semiconductor that we have will be p-type. That is more number of
P-type.
holes will be there. So what is the excess number of holes? That is whatever electrons and holes are equal, they will cancel each other out, right? They will become intrinsic itself. 10
Hmm.
power 15 and 10 power 16 here, both of them will suffice. Only some extra boron atoms will be there. So P value we will get by subtracting these two values. 10 power 16 minus 10 power 15, the P value we will get. And once you get the P value, you can find out the N value using the equation Ni square by P. So first, what is the P value? 10 power 16 minus 10 power 15 you have to do.
Nine into 10 power 15.
Yeah. So that will be the P value. Since Na is greater than Nd, it is a P-type semiconductor where P is equal to Na minus Nd, that is 9 into 10 power 15. Now you have got the value of P. Now you have to find the value of small n. And Ni is also given to you 10 power 10. So using Ni and P, you can find the value of n. N is equal to Ni square by P. So what will be the answer? So from here, if you see, you have two options. Out of these two, which will be the answer?
Option C, ma'am.
Yeah, 1.1 into 10 power 4 will be the answer. So whenever we are having a question where they are telling that the same material is being doped by both p-type and n-type, first equivalent numbers will get cancelled out and whatever is more, that will be the final semiconductor. Here boron was more, hence it was p-type, and the excess p, that is the excess number of holes, is obtained by subtracting them. And once you have the number of holes, you can find the number of electrons by using the equation Ni square by P. Suppose it was an n-type. Finally, if phosphorus was more and it was n-type, same logic you have to use. In that case, it will become Nd minus Na and you will find P using the value of n. That's all. So is it clear to you? The final answer will be option C. Yeah. I hope it's clear to
Yes,
both
ma'am.
of you. Yeah. Okay, now we can move on to next question. So again, intrinsic area concentration of silicon is given, Ni is given, electron and hole mobility is given to you. And silicon is doped with 10 power 15 phosphorus atom at 300 Kelvin and the dopants are completely ionized. You have to find the electrical conductivity. Here the material is doped only with one type of atom. But then also you have to find the values of N and P. Final material is n-type itself and n is directly given to you 10 power 15 and p value you have to find out, and once you have the value of n and p, you can use it to find the value of sigma. So out of this will be the answer. Please find out and let me know. So here mu e is given to us, mu h is given to us, n is directly given. And if you know n, you will get the value of p from ni square by n. So from that you have p and n, and finally you have to find the value of sigma. Sigma is equal to ne mu e plus pe mu h, right? So out of these four options, did you get any?
Is it B, ma'am?
I have to check. Then power 4, and finally, yeah, 0.216 ohm inverse centimeter inverse is the final answer. Yeah, it's correct. So basically, it's a very direct question. Only thing is that earlier it was a case of compensation doping. So we had to first decide whether it was P type or N type, and then find out which excess carriers were there. Here, nothing is that like that. You have to directly use whatever is given to you as N. That is the case. So I hope it's clear to you. So in that case, I think we can move on to,
Yes,
yeah,
madam.
we can move on to the next question. In an extrinsic semiconductor, the electron mobility due to impurity scattering is 300 and mobility due to lattice scattering is 200. What is the net mobility of electrons in the semiconductor? And give your answers in the same unit. So here we have some specific law that we are using. Can anybody tell me the name of the law? Total mobility will be sum of mobility due to impurity scattering and mobility due to lattice scattering. Yeah, one particular law we will be using here.
Is it mass action law, ma'am?
Yes.
Law of max flux.
Yeah. So this from the Mason's law, what we have 1 by mu.
Law.
Yeah. So 1 by mu E is equal to 1 by mu I plus 1 by mu L. So here they are asking, they have given us mu L and mu I. They are asking us to find out the value of mu E. So can you please substitute and let me know the answer? So 1 by 200 plus 1 by 300, you'll get one value, and after just take the inverse of that and you'll get.
120, ma'am.
Yeah. So it will
1
be,
by
yeah. Hence mu E will be 120 cm square V inverse and second inverse. Yeah. So next is consider the electrical conductivity of a p-type semiconductor at low dopant concentration. Its conductivity is given by normal equation E n E mu E plus P E mu P mu H. So at what Hall concentration the conductivity will be minimum? So what is the idea that we use here? We want to
You may
find
go
out.
ahead, madam.
Yeah.
It's
Hello?
okay to us.
Hello? Yeah, did you get this answer? Hello, am I audible? Hello, am I audible to both of you? Hello? So I think everybody has left due to the small delay due to a connectivity issue. So sorry for the delay, guys. There was some issue with my connectivity. So basically, this is the last question that I wanted to explain for today. Yeah. So basically, the question is that. So the next question is this. Consider the electrical conductivity of a p-type semiconductor at low dopant concentration. Its conductivity is given by sigma is equal to E n E mu E plus E mu P mu H. So at what Hall concentration will the conductivity will be minimum? So that is the question. So basically in mathematics, the concept that we use here, that is in order to find the Hall concentration when the conductivity is minimum, is that we have to take the derivative, and we have to take the derivative and then equate it to 0. So what is the thing that we should be taking the derivative with respect to? Here we have to find out the whole concentration at which the conductivity will be minimum. Hence we have to take the derivative with respect to the number of holes, that is P, and then after taking the derivative we have to equate it to 0. So to get the whole concentration at which conductivity will be minimum, find the derivative of the below equation with respect to P and equate to 0. So what we have to do, sigma is equal to E n mu E plus E P mu H we have to take, and in this particular equation we have to take the derivative with respect to P. That is, here if you see, you can see that we have taken d sigma by dp, and we are taking E as a constant, so therefore we are taking it outside, d by dp of n mu E plus P mu H. And again what we do here is that we are converting this n in terms of P. So we know that n is equal to ni square by P, right? So everything here is now derivable with respect to P. And now we take the derivative. So everybody know the derivative of 1 by P is equal to minus 1 by P square. That is how it becomes minus ni square P square by mu E plus the derivative of P is equal to 1. Therefore mu H. And once we have taken the derivative, that is, this is the derivative that we got over here. And once we have taken the derivative, we'll equate it to 0. And on equating it to 0, this E will get cancelled out, right? And when you bring this mu h to the other side, you will get something as ni square by p square mu e is equal to mu h. And from there we can find the value of p square as ni square by mu e by mu h. And finally p is equal to ni root of mu e by mu h. Therefore this is the whole concentration at which the conductivity will be minimum. So the basic idea is here is that the conductivity equation we have to derive with respect to P. Why do we derive with respect to P? We derive with respect to P because the whole concentration was asked. And finally, after deriving, we equate it to 0 in order to get the final whole concentration. So I hope this question is clear to all of you. So next is, consider the semi-log plot of carrier concentration versus inverse temperature for an intrinsic semiconductor, and the slot of the plot is proportional to what? So basically the semi-log plot they are asking, right? So carrier concentration versus inverse temperature for an intrinsic semiconductor is being asked over here. So how do we calculate that? We know that intrinsic carrier concentration is given by the equation root of NCNB e power minus Eg by 2 times Kb into T. So in order to compare the slope of this equation, we have to convert it into the type of y is equal to mx plus c, which is the equation for a straight line. So how do we do that? That is done by taking log on both sides. Therefore, ln ni is equal to ln of a product, that is ln a into b is equal to ln a plus ln b. Therefore, ln of root of NCNV plus ln of e power minus Eg by 2 kb into t. Since it is ln of e power something, it becomes Eg by 2 times kb into t. Sorry. And when you compare it with y is equal to mx plus c, how it will become? Y is equal to m into x plus c. Here they are asking it is versus carrier concentration at inverse temperature. Inverse temperature means that 1 by t is already here, and therefore y is equal to mx plus c, and in that case m or our slope will be minus Eg by 2 times kb into t. Therefore minus Eg by 2 times kb into t will give us the band gap. Hence we can say that comparing it with y is equal to mx plus c, the slope is proportional to the band gap. So that is the answer to this question. So finally, this was an this was a doubt from last assignment. So one person had requested me to answer this question. So molecular orbitals are filled in the order of increasing energy. Which of these principles do not govern how filling of molecular orbitals take place? So basically, we'll explain all these concepts one by one, and finally we'll come to the rule which doesn't involve itself in the filling of molecular orbitals. So first is Hund's rule. In Hund's rule, what happens? Hund's rules means that all the orbitals should be singly occupied before being doubly occupied. That is, instead of filling two at a time over here, initially all the orange ones has to be filled. And then again we have to go from this side and start filling the next set of electrons. It is not like at a time we can fill two electrons into one space. So that is the Hund's rule. That is, all orbitals should be singly occupied before being doubly occupied. So Hund's rule is used in molecular orbital filling. So next is Pauli's exclusion principle. Pauli's exclusion principle, we know that no two electrons can have the same set of all four quantum numbers. So first three quantum numbers, they can be same, and finally they cannot have the same spin. So correct will be they should be having opposite spin. Either this spin or this spin will be incorrect. That is what is happening in Pauli's exclusion principle. This is also followed in filling of molecular orbitals. So next we have the Madelung rule. That Madelung rule, what does it do? It tries to establish the order in which electrons fill in the sublevels of atom. Like we know that Aufbau principle, electrons will always occupy from lowest energy, and when we are measuring the energy of these orbitals, it will be 1s1, 1s, 2s, 2p, 3s, then 3p and 4s. Instead of 3d, we know that 4s will come, and then 3d will come, 4p, 5s. So this is the order in which the electrons will be filling in the subshells. That is given by the Madelung rule. Therefore, all these three rules, Hund's rule, Pauli's exclusion principle, and Madelung rule, will be used in filling of molecular orbitals. So next is Heisenberg uncertainty principle. Heisenberg uncertainty principle says that it is impossible to measure or calculate exactly the position and momentum of an object. So it is based on the wave particle duality of matter. We know that for deriving molecular orbitals, we use the Heisenberg uncertainty principle and wave functions. But be very specifically, if you observe this question, they are asking which of these principles do not govern how the filling of molecular orbitals take place. So that is the key word over here. If they are asking that it is the formation of molecular orbitals, then Heisenberg uncertainty principle would have been an answer. Here they are not concerned about formation, they are concerned only about filling. So when we are talking about filling, the only three rules that matter are Pauli's exclusion principle, Madelung energy ordering rule, and Hund's rule. Therefore, the principle that does not govern over here is the Heisenberg uncertainty principle. Therefore, though this principle is associated with the formation of molecular orbitals, they do not govern the filling of these orbitals. So, thank you for your kind attention. Please post additional questions in the discussion forum or directly mail me at santra.pmrf@gmail.com. Thank you for spending your time with me. So, Sam, hoping to see you next week. So, thank you very much and goodbye.